Good day, students, and come with me as we take these likely NABTEB physics past questions. Moving on to the first question. Question number 1 says, state Hooke's law. Hooke's law states that provided the elastic limit of a material is not exceeded, the force applied is directly proportional to the extension of the material. This law was stated by Robert Hooke, and if you remember Robert Hooke was also the one that first discovered what the cell, and he stated this law also, which is the force applied is directly proportional to the extension. So what Sir Hooke was saying is that when you apply a force to an elastic material, that this force is directly proportional to the extension of the material. So if you have any sign of proportionality in physics, what you do is what? Introduce a constant. So if I introduce my constant, this means that my F is equals to KE, where F is force, KE, or you can also say KX, this can also be written as KE, where E or X is extension, and K is my constant. So when you are solving for the Hooke's law, so our Hooke's constant here is K, because we are using it as what our constant in this particular word explanation for Hooke's law, which was stated by Robert Hooke. Question number 1b, which says a elliptical spring is stretched by loading it gradually with increasing weight, and the corresponding extension recorded until the elastic limit is reached. Draw a graph of load against extension showing the following. Remember figure 1, elastic limit. Remember figure 2, yield point. And remember figure 3, breaking point. So when Sir Hooke did his experiment, he came up with a graph. This is load, measured in Newton, and this is extension, measured in meters or centimeters. So Sir Hooke drew a graph that looks like this. So at this point, so in this graph, you discover that when you start stretching an elastic material, it continues to what? Increase until it gets to a point we call the elastic limit. So this is the elastic limit. And then we get to another point we call the yield point. And then lastly, we'll get to another point we call the breaking point. So what are these points? The elastic limit that Robert Hooke explained is the point where an elastic material still retains its original form. That means there is no deformation when you stretch that particular elastic material, when it is still within the elastic limit. While the yield point is that point where that material no longer returns to its original form. There is now slight deformation in the physical structure of that elastic material. And the breaking point is that point where the elastic material has gone to its maximum load. It can no longer contain the amount of force or load you are applying on it, and it ruptures or cuts or breaks. That's why we call it the breaking point. For example, if you have a rubber band and then you are stretching it, you discover that after some time, the rubber band no longer have that exact same structure it was having when you first got the rubber band. That point where it's no longer having that exact same structure is what we call the yielding point or the yield point. Why that point where it returns to its original form after stretching it is what? My elastic limit. And the point where it can no longer contain the amount of force you are applying is what we call the breaking point. Moving on to question number 1c. It says, if a spring has a stiffness of 1000 Newton per meter, stiffness is also called our force constant, which is what? Hooke's constant. We call it what? The degree of stiffness, which is what? K. So our K in this question is 1000 Newton per meter. They said, what work will be done by extending the spring by 100 millimeters. So we're looking, the extension here is 100 millimeters, and then they're asking us what is the work done. We do not know. So we know that our 100 millimeters cannot remain as 100 millimeters, so I'm going to convert it to be in meters. This is the same thing as saying, because if you look at our unit here, our force constant or our degree of stiffness is Newton per meter, which means the original unit of our extension should be in what? Meters. So I have to convert my 100 millimeters to be in meters, which means that my extension is 100 divided by 1000, because milli means times 10 raised to the power minus 3. So this will give me 0.1 meters. Okay, so 0.1 is the same as in I have what? 1/10 meters. So moving on, we know that our work done in an elastic material is equal to half kx squared. Half kx squared. So this is the same thing as saying that I have 1/2 times my k here is 1000 times my x here is 1/10 or squared. So this will give me 2 here 1, 2 here 500. So this will give me 500 times 1/100. So this 2 0 here will cancel out this 2 0, and that will give me 5 joules. So the answer to this question number 1C is 5 joules. So that takes us to question number 2AI. Question number 2AI says define cubic expansivity of a gas at constant pressure. Define cubic expansivity of a gas at constant pressure. The cubic expansivity of a gas at constant pressure is the increase in volume per unit volume per degree rise in temperature at constant pressure. What does this mean? Cubic expansivity is represented or denoted with gamma, and it is equals to increase in volume divided by volume times change in temperature or increase in temperature. This is the same as saying that my gamma is equals to change in volume over volume change in temperature, which can be rewritten as saying V2 minus V1 over V1, open a bracket, theta 2 minus theta 1, where gamma is used to represent cubic expansivity, V2 is final volume, V1 is initial volume, theta 2 is final temperature, and theta 1 is initial temperature. So please note that all expansivities are measured in per Kelvin, and the reason is because volume here is measured in meters cube divided by volume, which is also what? Meters cube. So meters cube will cancel meters cube, and I'll be left only with what? Temperature. And because the temperature is in the denominator, it means that what? My cubic expansivity, my linear expansivity, and my area expansivity, which are following the same format, are what? Measured in per Kelvin. Per Kelvin. That is the what? Unit. So that takes us to question number 2AII. 2AII says, explain why it is necessary to leave gaps between steel bars used in constructing railway lines. Now, the reason why there are usually gaps when what? Constructing railway lines within the steel bars is due to what? Expansion. The gap there is left for what? Expansion of the bars. So there is usually what? Expansion when there is increase in temperature. So the gaps are left for what? Expansion when there is what? Increase in temperature. Because whenever there is increase in temperature, there is going to be what? Increase in the length of the steel bar. So those gaps are left there for the expansion. If gaps are not left, after the expansion, there will be what? Shifting of the what? Bars. Hence, it will lead to what? Accident on railways. So hence that gaps were left. there for expansion. Moving on to question number 2b, it said describe an experiment which could be in the laboratory to show that the volume of 30 grams of oxygen at constant pressure changes by 1/273 of its volume at 0 degrees Celsius whenever its temperature changes by 1 degree Celsius. Now, for you to do this experiment, the procedure, you're going to need about 30 grams of oxygen placed in a tube that is with a uniform bore. What do I mean? So I have a tube like this. So here I have my oxygen. And then here I have mercury placed within the what? The tube. So I have to bore a hole in that tube such that since the tube is uniform, then I put mercury pellets within this other part of this tube, such that when I start hitting this particular oxygen oxygen within the tube, the mercury will start expanding. And as the mercury is expanding, I will note the original volume and the original temperature before I start heating. So I'll put it inside a water bath. I have to put it inside a beaker containing water. So I put it inside a beaker containing water so that I do not heat the tube directly, but I heat the beaker. So when I'm heating this beaker with water in it, the temperature of the water will be reflected within the oxygen, and it will be also reflected in the mercury pellet, so that the mercury pellet will start increasing. So at this point, this is the point where it is 0 degrees Celsius. And this is the point where it will start expanding uniformly. So when you start heating it, you discover that the mercury pellet will start increasing. And as the mercury pellet is increasing, it means that the volume of the oxygen present is also increasing proportionally as they are kept within the same uniform bore of tube. So as the volume of the mercury is increasing, you can easily measure the increase in the volume of the oxygen present. So this phenomenon is bordering on cubic expansivity. So what do I mean? So at the end of the day, you know that your cubic expansivity is supposed to give me change in volume over volume change in temperature. This is the same thing as saying that I have change in my cubic expansivity is volume all over volume change in temperature. And my change in temperature, as in this case, is measured in Kelvin. So since it is measured in Kelvin, this means that my change in temperature is equals to 273 Kelvin. So this can be written to say that my cubic expansivity is equals to the volume all over the volume times 273, which is the same as saying that volume will cancel out volume. It means that my cubic expansivity is 1 over 273. So what this simply means is that an increase in the volume can be reflected or can be expressed in the form of 1 over 273 of its volume at 0 degree Celsius. So this experiment is just used to demonstrate the change in the volume of oxygen of about 30 grams and comparing it with change in temperature of 1 over 273 Kelvin. Moving on to question number 2C. It says a bimetallic strip of brass and aluminum is 20 centimeter long. So the original length of both brass and aluminum here is 20 centimeter. So at room temperature, what will be the difference in their length when the temperature is 20 degrees Celsius above room temperature? So we know that they are asking us to find the change in temperature between brass and that of aluminum, since it is a bimetallic strip. So they are joined together. but they are going to what expand differently due to their differences in linear expansivity. So we know that the change in temperature here is supposed to give me 20 degrees Celsius. So we know that alpha for aluminium is 0.00015 per Kelvin, and that of brass is 0.00019 per Kelvin. So we know that the linear expansivity is supposed to give us change in length all over length change in temperature. So for brass, I'm going to have 0.00019 is equals to change in length all over 20 times 20. And that will give me that my change in length is equals to 0.00019 times 400. And that will give me 0.076 centimeters. So for aluminium, I'll have 0.000015 is equals to change in length all over 20 times 20, which means that my change in length here is going to give me 0.000015 times 400, and that will give me 0.006. So the difference in their length, therefore, is supposed to give me difference in the length of brass minus difference in the length of aluminium. So that is to say that I have 0.076 minus 0.006, and that will give me 0.07 centimeters. So at the end of the day, the answer to this question is 0.07 centimeters. Moving on to question number 3a, it says, with the aid of a well-labeled diagram, describe the eclipse of the sun. So eclipse of the sun happens when the moon comes between the sun and the earth. So if this is the sun, and this is the earth, then this is the moon. So I have the diagram looking like this. So this is moon and this is earth. Now, what is eclipse of the sun? When the moon casts its shadow on the earth by obstructing the rays of sun from getting directly to the earth. So when the ray of sun passes through the middle of the moon before getting down to the earth, is called what? Eclipse of the sun. And this happens when the moon blocks the ray of light from reaching the earth directly. So on this part here is the umbra. This is the umbra. While this part, we have the penumbra. This part will also have the penumbra. Now, when this ray of light coming from the sun is obstructed by the moon before getting to the earth, thereby the moon casting its shadow on the earth. So when the moon is casting its shadow on the earth, as a result of what? Obstructing the ray of light from the sun from getting to the earth, is called what? Eclipse of the sun. And this way, the part where the moon is casting its shadow directly is going to form what? A very thick shadow. And that shadow, because it is very thick and dark, it is called what? Umbra. while the penumbra is not as thick as the umbra, is the light shadow that is casted upon the earth. So this phenomenon whereby the moon is casting its shadow on the earth, thereby obstructing the ray of light from the sun from reaching the earth directly, is called what? Eclipse of the sun. So question number 3B is the next question. 3B, I said, explain the principle of operation of a pinhole camera. Explain the principle of operation of a pinhole camera. So this is a pinhole camera. A pinhole camera is just a box so inside the box, the walls of the box are painted black so as to what? Absorb rays of light that are what? Straight. So if I have an object, let's say I have a human standing here. So the pinhole camera is going to what? Reflect this on a photographic plate. So there's a photographic plate at the back of the pinhole camera. At this part of the pinhole camera, we have a photographic plate. So here we have a photographic plate. So this aperture, this small opening of this pinhole allows light to pass straight, while this part or the other side of this pinhole are painted black to what? Absorb ray of light that are what? Straight into this pinhole camera. So the pinhole has a phenomenon of what? Inverting any object that is what? Pictured by it on the photographic plate, such that if this is the object, you discover that the pinhole is going to reflect it this way, such that this will become, this is how your object will look, to become diminished, and at the same time, it will be reflected this way. So this is how your object will start looking on the pinhole camera. So the pinhole camera is going to what? Turn it upside down. That is what? Laterally inverting it. So this phenomenon of using this box to what? View an object and have it captured on the photographic plate is the phenomenon or the principle of the pinhole camera. So the pinhole camera what? Inverts the object and what? Place it on the photographic plate. So what are the disadvantages, which is the next question? Say, what is the main disadvantage of the pinhole camera? One of the main disadvantages of the pinhole camera is that it inverts the object. It inverts the object. It laterally inverts the object. The second advantage, or another advantage of the pinhole camera, is that it takes time for the pinhole camera to form the image on the photographic plate. It takes time for the pinhole camera to form the image on the photographic plate. Another disadvantage of the pinhole camera is that if the aperture is wide, the image will be blurry. If the aperture is wide, the image will be blurry. But when the aperture is small, the image will be sharp, but it will be darkened. It will be sharp and darkened because there's not enough light within the pinhole camera. So these are the disadvantages of the pinhole camera. Moving on to question number 3C. It says an object 50 centimeters tall. So the object height is 50 centimeters. It's placed in front of a pinhole camera, 1 meter away. So the object distance is 1 meter from the camera of length. So the image length, image distance. So the image distance here is 20 centimeters. Calculate the height of the image. So we're looking for image height. We do not know. So that's the first part of the question. Calculate the height of the image and its magnification. So the height of the image, that's the first thing we're supposed to look for. We know that image height over object height is equals to image distance over object distance. So with this means that my image height, which is unknown, over my object height here is 50 centimeters is equal to my image distance is 20 centimeters over my object distance is 1 meters, which is 100 centimeters. So I have over 100. So if I cross multiply here, it means I have 100. Image height is equals to 1000. So if I divide both sides by 100 divided by 100, this means that my image height here is 10 centimeters. So the image height is 10 centimeters. Then they say calculate the magnification. We know that our magnification is image height over object height. So in this case, that will give me 10 centimeters over 50 centimeters, and that will give me 0.2. So the magnification here is 0.2. So since I've gotten my magnification, then I will go for that. The question said, if the object distance is doubled, what will this affect the size? How will this affect the size and magnification of the object produced? Now, if the object distance is doubled, when the object distance increases, then the image height will reduce, because the object distance is increasing, the image height is what? Reducing. And the magnification will also reduce. So long as the image height is reducing, the magnification will also reduce. So next question, which is question number 4a, says distinguish between electric conductors and insulators and give 4 examples of each. Electric conductors and insulators. Now, what is an electric conductor? An electric conductor is any conductor that allows charges to pass through it, that allows charges or electrons to pass through it. Any conductor that allows electrons to pass through it is called an electric conductor. While the one that does not allow charges to pass through it, or that does not allow the flow of electrons, is called an insulator. What are the examples of electric conductor? An example of electric conductor is your metals. All metals are generally conductors of both heat and electricity. We also have another conductor such as what? Salt solution. They are also what? Good conductors of electricity. Other conductors could also include your acids. Solutions of acid are also good conductors of electricity. Another conductor is the human body. Current can also pass through the human body. That's also what? Another example of a good conductor. Examples of your insulators include your non-metals such as sulfur. They are what? Used as insulators. Other examples of insulators include paper, cloth, your ties, and etc. That takes us to question number 4b. Question number 4b says, what is a capacitor? Name 3 types of capacitor and 3 appliances that can use capacitor for operation. Now, first, what is a capacitor? A capacitor is a device that stores charges. You could also say that a capacitor is a device that stores electricity. So capacitor generally stores charges. And what are the types of capacitor? We have the variable air capacitor, we have the electrolytic capacitor, and we have the paper capacitor. These are the 3 types of capacitor. And what are the appliances that you can use your capacitor? You can see your capacitor in the starter of your pumping machine, your water pumping machine. We have what? A capacitor there. You can also find your capacitor in the your car's ignition system. When you want to start your car, you also have a capacitor there. You also have your capacitor in your electric fans. You have your capacitors also present in your electric fans. So you can find your capacitors in many electrical appliances. Capacitors are generally present as well starters in those electrical appliances. So that takes us to question number 4C, which I have here as a diagram. So I have a diagram this way. So I have, in this diagram, I have a capacitor here. Then I have another capacitor here. Then I have a capacitor in between. And then I have my voltmeter connected. So this is what I have in the diagram, and this is 1.5 microfarad. This is 2 microfarad, and this is 5 microfarad. This is 20 volts. So the question says, calculate the effective capacitance. So the first part of the question says, calculate the effective capacitance, which means that we have to calculate the capacitors that are arranged in series and the capacitors that are arranged in parallel. Now, if you look at this, if your voltage is coming this way and it gets to this point here, you discover that what? This point here, they are having what? A split. So at this point here, it means that these two capacitors here are connected in parallel. And we know that what? In the arrangement of capacitors, the parallel arrangement of capacitors is the same as series arrangement of resistors. So it means that if I say this is C1 and this is C2 and this is C3, this means that the first part, the parallel arrangement, for parallel arrangement, it means that the C of my parallel arrangement is C2 plus C3. This means that I have 2 microfarad plus 5 microfarad, which will give me 7 microfarad. So the total capacitance of the capacitor connected in parallel is 7 microfarad. So if you resolve that, you'll be having a diagram that looks exactly like this. So you'll be having something like this, so that they are both now in parallel. They are both now connected in series, sorry. So this is volts, and I'll be having something like this. So I've resolved these two here to become what? Series connection. So this is 7 microfarad, and this is 1.5 microfarad. So since I've resolved this to be in series, so I have, this is what? 1.5 microfarad. So I will not solve this using the what? Series formula, which says that I have what? My C total here will give me what? C1 times C2 over C1 plus C2, which means that I'll be having 1.5 times 7 over 1.5 plus 7. So if I do this, this will give me 1.5 times 7. That will give me 10.5 over 1.5 plus 7 will give me 8.5. So if I divide this by 8.5, it means I'll be having 1.24 microfarad. So it means that the total effective capacitance in this particular connection is 1.24 microfarad. So the question number 4CII says, what is the charge? Calculate the charge on C2 and C3. Calculate the charge on C2 and C3. So we know that our formula says, formula for charge, for Roman figure 2, formula for charge says that my Q is equal to what? CV. So, and I know that whenever anything is connected in parallel, that the voltage through them is the same. But when they are connected in series, that the voltage differs. So for C2, as in this question, my C2 has a capacitance of 2 microfarad. So it means that the quantity of charge passing through it is going to give me 2 times 10 raised to power minus 6 times my voltage in this particular question is 20. This means that I have what? This will give me 4 times 10 raised to power minus 6 times 10 raised to power 1, and that will give me 4 times 10 raised to power minus 5 coulomb. So that is for what? C2. I'll also find the what? The charge on C3 as in the question. So the charge on C3, the charge on C3, since my C3 is 5 microfarad, so it means that my charge on C3 is going to give me CV, and that will give me 5 times 10 raised to power minus 6, 5 times 10 raised to power minus 6 as the capacitance. So I have 5 times 10 raised to power minus 6 as the capacitance, times the voltage in this question is 20. So that will give me 100 times 10 raised to power minus 6, which is the same as saying I have 1 times 10 raised to power minus 4 coulomb. So the question then says, what is the energy in the circuit? What is the energy in the circuit? So in the circuit, the formula for calculating the energy says that I have, that's Roman figure 3. So for my Roman figure 3, they said what is the energy in the circuit? And we know that the formula for calculating the energy says that the work done in an electric circuit is equal to half CV squared. So this is the formula for calculating the energy in a circuit containing capacitors. So this will give me 1/2 times my total effective capacitance here was 1.24 times 10 raised to power minus 6 times my total voltage was 20. So I have a 20 squared. So this will give me 1/2 times 1.24 times 10 raised to power minus 6 times 20 squared will give me 400. So 2 here 1, 2 here 200. So if I have 1.24 times 200, that will give me 248 times 10 raised to power minus 6. So if I put this in accurate standard form, I'll be having 2.48 times 10 raised to power minus 4. And because I'm talking about work done, this will become joules. So that is the correct answer to question number 4C. We've come to the end of today's session. Don't forget to subscribe, and if you have any question, drop it in the comment section below.